Okay, so in this problem, I'm going to give you some background. So the first thing I want you to understand what a resistor is. Okay, let's say we have ourselves a conductor. Okay, and of course this conductor is connected to some kind of battery. Actually, it doesn't even need to be this way, but this is the idea because we're looking at the resistance. It's a property of the material, so you don't have to have a voltage on here. Okay. But when you put the voltage on here, it gives rise to what the resistance is going to be about. It's going to resist the flow of current, or it's going to show you how things are going to change from electrical energy to heat energy. This is the idea. So this is our R. This is the same representation can be done like so. That's what this is. All right. Delta V. All right. So this R or this conductor has a length associated with it. It has a cross-sectional area, and I don't know why I'm not using some other color. So it has a length associated with it. It has a cross-sectional area associated with it, which in this case is just going to be pi r squared, r be, being the radius, okay? This is r. It's the radius of the cross section. However you need to do the area in whatever geometrical configuration you have. It's as if you cut the wire directly down its um, you cut it in half, okay, and it's long in the lengthwise form. And then we have another property, and it's called the resistivity. Okay, so the resistivity is a property of different kinds of tables. If I bring up resistivity table, what you'll see, let me see, I usually, here's hyperphysics, we could use that. You'll see that you have the resistivity in ohms times a meter for different things, silver, copper annealed, they're very close, aluminum, tungsten, iron, on and on and on. And of course, I mean, you could do this work yourself, but here's a table. I think it is instructive for you to do it yourself. Let me see. Here's another table, or it breaks down. Well, here's another table right here. So I don't like all those things. Okay. Of course, you can go to Wikipedia. You can go to other locations here. It was the engineering toolbox, which I often refer to. So you have an engineering toolbox here. Okay, and it gives you the resistivity coefficient, all right, as well as conductivity, where conductivity is just the inverse of resistivity. Okay, so you'll see all of that information. You can see that the table is much more extensive here. Let me go back to this. Okay, so you need to know the material that you have, all right, and you need to know the length as well as the cross-sectional area. And with that, you can find the resistance based on static parameters. Okay, and this is just the area. Okay, so we can calculate the resistance here. Now, if we take this and we put these two resist, well, I'll just say that, let me say this, the longer the resistor is, okay, the greater the resistivity. I'm sorry, the greater the resistance is going to be. So if the length increases, the resistance increases. All right, typically we write this as if the length increases, the resistance increases. Okay, if the area increases, the resistance decreases. All right, so that's what's meant by directly proportional. These two are directly proportional, and these two are inversely proportional. All right. So now that you understand the configuration or the static representation for resistance, now let's look at resistors in series. So if we put two resistors like so in series, you have R1, you have R2. The way we write this is like so. If we say the total resistance in this case, RT is going to be equal to R1 plus R2. Okay, that's just the skinny of it all. Okay, so we have our first, um, and I'm going to put an S here. I'll put an S here for total in series, and I'm just going to say equals to R sub 1 plus R sub 2. All right. Now, if we keep adding resistors, okay, to this, then this will be plus dot 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 plus R to the n. So if I added another resistor R to the n, it will deal with all resistors in series. It's not just going to be R1 plus R2 plus, I mean, and then and that's all. Okay. So now I am going to do this. If I have resistors in parallel, okay, and I call this R3, and I call this R4. Now, I want you to know something that this R sub 1 has an L sub 1, and then we have an L sub 2. So the way I want you to think about this is if you look at this equation right here, we're effectively increasing the length. Thus, this implies that the resistance is going to increase. Okay? In this particular case, we are effectively increasing, and I'm just going to say area 3, area 4. We are effectively increasing the area of our resistor. Okay? And so um, I can just go here and I can say, oh, A sub 1, and I'm still doing A sub 1, A sub 3 plus A sub 4. This is going to imply that resistance will um, decrease because as the area increases, the resistance drops. Okay, so what I'm going to do right now is I'm going to stop this video and I'll make a part 2 to it.